All right. Should I start?
Yes.
All right. Good morning, everyone. I think I was introduced well by Olivia, so I leave it at there. Today, I'm going to talk a little bit about data-driven agriculture and how we research and use these tools for improving a specialty crop production, basically in California. And I know that Chile has a very similar agriculture, just opposite season. So many of this information, I believe, would be beneficial for Chilean specialty crop as well. So let me start by talking a little bit about the concept of digital agriculture and precision agriculture. And then I'll talk a little bit about the tools and technologies and models that we're using. And at the end, I will talk about 3 case studies, one of them for table grape, one for almond, and the third one for citrus, and how we use this technology for these 3 different specialty crops. So digital agriculture integrates all advanced type of data collection and data interpretation models to enhance agricultural production system. That includes from collecting the data all the way to generating some output that can be used as a practical knowledge or as an insight for the growers so they can make a better decision. I'm not sure if you're familiar with the concept of precision agriculture, so I'm going to go over that pretty quickly. Growers usually use precision agriculture to harness the power of science and technology that improve their productivity. This can be done in many different ways. For example, GPS-equipped combines can be used to harvest crop and measure yield as they harvest. So they can generate a map that shows the yield variability within the field. Yield variability would be the starting point of precision agriculture, because that's actually the big problem if we have field variability. We would like our orchard or our farm to have a uniform yield. So if there is yield variability, means some part of the orchard does not function as well as the rest, and we need to find the problem, resolve that, and that way we can improve the yield and profit. Another way of using precision agriculture is to do soil sampling at different part of the field. So that is not new. Soil sampling has been done for a long time, but precision agriculture provides the opportunity to do a very precise and large scale and high resolution soil mapping that will improve the quality of your data and then improve the quality of result. Another example is to check the weather data and incorporate the prediction of weather into your crop management models. So these are some kind of data that we collect. I will introduce more type of data that will be generated through remote sensing. The next step is to do data analytics. So after we collected all this data and we granted it with some measurement in the field, we can develop some analytic tool that can predict the unknown points of the orchard. For example, if we have 10-acre table grape, we never will be able to sample all vines in this vineyard. We can do maybe for a few vines, and currently growers just use that few vines to make the decision for the entire vineyard. But remote sensing will get those a few points and then expand that to the entire orchard. So you will have an insight of, for example, disease or water stress in the entire vineyard or orchard. That is called prescription map. Prescription map is tell you a lot of information about what's going on in your field. So as we go forward, we will collect more and more data, and we will be needing some data management tools to organize all this data. And many of these data are not useful. So we need to find what type of data is useful and then store that and save that for future. Okay, so now we know what's going on in the orchard by collecting data and interpret them. Now it's time to apply in a site-specific or precise manner. If we know that some part of our vineyard doesn't need, for example, nitrogen, we don't need to apply excessive amount of nitrogen. That would contaminate the soil and water, and that would have a negative impact on the yield. So if we know, for example, a portion of our field doesn't need nitrogen, or a portion severely stressed by nitrogen and needs a lot of nitrogen, we can use that to employ a variable rate applicator that reads the prescription map and finds its location in the field, and it knows exactly how much input should be applied to each zone or to each parcel, or basically depends on how you divide your field. So this is basic steps, 3 steps in applying precision agriculture. If we want to look at it at the big picture, again, precision agriculture starts with yield, because we want to have a uniform orchard, uniform yield that will guarantee that we get the maximum possible profit from the orchard. But it's a cycle. So the first part of this cycle, we will do sensing. That includes soil sensing, aerial imaging, satellite imaging, and also some field scouting or ground truthing. For that, we need to send agronomist or plant pathologist or water specialist to the field to see what's the problem is. And so basically we can validate and calibrate our aerial data using ground truth. I will have a lot of slides about that, so this is just the introduction. The most important part of this cycle that is missing right now and prevents the industry to use effectively the precision agriculture and digital agriculture tools is the data interpretation models. Collecting a lot of data is good, but it's important that we interpret and translate this data in an accurate way. If we don't do this in an accurate way, that will lead to some misguiding insight that not only it wouldn't improve the productivity, it will have a negative impact. So we need to make sure that we have some accurate interpretation models that can convert the data that we collect from the field into some actionable, practical knowledge that would be actually beneficial for the growers. I will explain how we would do that. And last step is the site-specific application, as I mentioned. So now we have all this good data, and we have this intelligent model that can tell me exactly what's going on at each part of in my orchard. So now what? What should I do now? That's also another challenge that we are facing and we are trying to solve. And we need the tools that can apply variable rate application for inputs. For example, we can apply variable rate of nitrogen or water. So in a specialty crops, in low crops, it's pretty established because the entire orchard is, the entire field is similar. It's a very big field, and it's mostly mechanized. So when farm is mostly mechanized, we can add intelligent device, electronic device, to make it able to do adjustment on the go. So if we enter a zone that requires more nitrogen, the applicator can adjust to our to provide more nitrogen. But in the specialty crops, usually there are not many mechanizations. So, for example, nitrogen or application or all nutrition goes through the irrigation line. So, if we have precise irrigation, precision irrigation application, we can do precision nutrition as well. But if we don't, we cannot do that. So that requires some renewing some infrastructure, but still it will give you a lot of good information that may lead to some new decision that you never think about it. So let's talk about it. Well, the portion of digital agriculture that my lab focus more is remote sensing through drones and UAVs. We realize that this might be the best and most available tool compared to satellite imagery and compared to manned aircraft imagery, because it's getting very cheap and more affordable. So now you can buy a drone for less than $1,000 and monitor your field easily. So that wouldn't be possible a few years ago. That opens a lot of new doors. The ability of looking at your field from above, that ability itself will provide a lot of good information. But let's see what else we can see. So remote sensing in general is the science of acquiring information from Earth's surface, and that happens without touching or being in contact with the object. And remote sensing has a lot of use in different industries, but it's growing very fast in agriculture, and many growers and industry are usually tending to use this technology these days. Okay, so as I mentioned, just looking from above will give you a lot of good insight. But what if you can look at the at your orchard in non-visible bands? In other words, trying to find something that is not visible with human eye. We know that human eye can only see within the visible range from about 400 nanometers to 700 nanometers. Anything beyond this wavelengths in the electromagnetic spectrum is invisible. In other words, we are blind to that. But we know that in the infrared and near infrared region of the electromagnetic spectrum, there is a lot of good information about plant health. And if we could see that, we could reveal a lot of details about how the plant is doing. So this is also another part of the electromagnetic. It's called the UV. That also has some good information. This is the part that we usually see, and this is the part that we don't see, and there is a lot of good information in that part too. So I briefly talked about the spectral signature. So like any other human who has a signature and that signature is associated with them, we can detect object on the ground based on the spectral signature. So let's see how it works. So plant usually, when a light intercept the plant, there are different events that can happen. Some part of that light can go through, some part can reflect, and some part can be absorbed by the plant. In remote sensing, we usually work with the reflectance. We want to see how much of the light that we are providing is reflected, and by measuring that, we can have an estimation of what's going on in the plant. That will be done in a very high spectral resolution. So we can do measurement at different wavelength and then plot the measurement. So for example, for dry vegetation, we know that they look green. So they have a peak around green and they have some valley in blue and red area. But we can see that they also have a very big peak in near infrared that is not visible. Using spectral sensors, we can make these different signatures for different objects and then separate them. Again, we only see this part of the electromagnetic spectrum. So whatever happens in this region, we are blind to that, and there is a lot happening in that region, I can tell you. One index that can be, measure that can be used is the normalized vegetation index. So normalized vegetation index actually compares the near infrared part to the red band. And if this distance is bigger, means we have a healthier plant. If it's smaller, means we have a problem. So this is an Ndvi of the world. We can see where most of the vegetation happens. And so, for example, here is California, and we can see that in California we have desert, we have agricultural area, we have the Central Valley, and I think this part would be Chile, mostly red, so there are not many vegetation like Amazon or like East United States or South Africa or Central Africa. So these images can be generated by satellite imagery. So I explained a little bit about Ndvi. Ndvi varies between -1 to 1, and below 0 is usually soil or ice or snow. Above 0.4 is usually vegetation, and as it gets closer to 1, we have more dense vegetation. But I'll tell you, this is a conventional method in remote sensing. So that's what used to be a method for people, but right now there are more complicated and more advanced methods for that, and I will talk about that. So this is the formula to calculate Ndvi, measurement in near infrared minus red channel over a measurement of near infrared plus red channel. And that will be normalized value between -1 to 1. So as I mentioned, below 0.1 is area for rock and snow. So Ndvi is available for free if you go to satellite imagery, free satellite imagery like Landsat. The resolution is not good, it's about 30 meters, but if you find a way to access to those Ndvi imagery, you can use these values to see what's going on. So value below 0.1 is not agriculture. Between 0.2 and 0.5 would be a sparse vegetation like grassland, not agricultural area. But usually over 0.5 to 9 is dense vegetation, and more Ndvi means more money usually, because it means more vegetation and more yield. This is a comparison of how the 3 different remote sensing platforms, satellite, aircraft, and drone. And so any of these platforms have their own advantages. Satellite can scan a large area in a very small time, and it can repeat that. Aircraft, it would be closer to Earth, so it can generate higher spatial resolution imagery, but it's a little bit expensive. Drone generates the most high resolution imagery, but you cannot cover a very wide area in short time. So So these are the trade-off between different platforms. Specialty crops, unlike the row crops, usually specialty crops are in a smaller blocks, maybe about 40-acre blocks. So drone would be a very good option for a specialty crop. But for row crops that the acreage can go over 100 or 200 acres for one block, satellite or aircraft might be a better option. It can be used for different applications: stress detection, monitoring the growth, estimating yield, which is a very favorable application these days, optimizing nutrition by detecting the nutrition stress, optimizing the water application by finding the water stress or well-watered area, and applying herbicide and pesticide in a precise manner. Okay, so that was an introduction. Now let's get into what we are doing in Digital Agriculture Lab at UC Davis. This is an overall pipeline from beginning to start, what we do here. So as you see, the first step is always start with data collection. We collect aerial data with different platforms like LiDAR, RGB, hyperspectral, multispectral, and thermal. And we also collect some ground truth data from the same field at the same time. That is actually the key to solve the problem. Those ground truth data will be used to pair the aerial data to that ground truth data, and then using a few samples, we can interpolate or extrapolate to the entire vineyard or entire orchard. I will explain about that. The second step is pre-processing. That's a very important step, because if we don't do that right, we may come up with a wrong conclusion. That includes calibration, radiometric calibration, and also generating orthomosaic and georeferencing different layers that I will talk about it. The third step is processing. Now we have some good data. We need to extract some features out of that data. That will include identifying individual plant in the image, segmenting and removing noise, and then extracting features like canopy size, canopy spectral reflectance at different bands, and vegetation indices. The fourth step is analytics. We use data analytics these days for anything, for defense, for medicine, for industry. And you know that Bay Area is the center, in San Francisco area is the center for data science. There are a lot of data science companies there, and they're using analytics for different approaches. But it's not used extensively in agriculture. So we don't have any problem in analytics, because there are a lot of people working on that, and it's a very fast growing field. But we need to find out the best tool that would work for agriculture. So after processing, we get all of this data. We need to investigate the data to find which of these data are relevant, which of these data are not useful. That's feature engineering. And then we use classification model, machine learning algorithms to regress or classify, to train first, and then classify the unknown samples, in this case, unknown plants and what's going on. The fifth step, we use the output of all the last four steps in application. So how can we use? We can monitor plants during the field, during the growing season, and if some part of the orchard is going wrong, or there is something wrong, we can find it out early and just take care of that before it results in a low yield area or some damage that cannot be recovered later. But another thing is the insight that this will give to the growers. we don't want these models to make decision on behalf of the growers, but we will expect that to provide some insight, some more accurate insight for growers. So the growers can use that to make better decision. And I will tell you how. So let's start with data collection. We can use a different platform depending on our application and the size of our orchard. For data collection, we can use fixed wing that would fly higher and faster and can cover bigger area, but it has a lot of limitation. We can use the quadcopters that we have a lot of control on them. And as you see, every day we have higher, advanced, and less expensive drones. For example, these two drones by DJI are very inexpensive. This one is, for example, a multi-spectral camera, all built in one drone. So you just take it out and fly. You don't need to do any setting. And so this is what we have now, but in future, I'm sure we will have more and more better products. And these are different type of sensor we can use. There's the hyperspectral sensor, for example, on the lower right, thermal sensor, and multispectral sensor that can reveal the image of the plant in non-visible bands. This is, for example, one of the sensors that we use is a drone that can carry two sensors, one multispectral and one thermal camera. And so this multispectral camera can measure in blue, green, red. That's what we can see. It also measures red edge and near infrared. That's the invisible band that we don't see. And these are two important bands for assessing plant health. We use different type of flight mission planner for different application. This is one example. So when we have a drone and we have a camera, we don't need to control it. Olivia, can you mute everyone else but me?
Yes. So Natalia, she's the host. So I was just texting her.
Thank you. So we can use different flight mission application. This is something that we use mostly. It's a Pix4D capture. It's a free application that you can use on your iPhone or tablet. And you can, for example, plan a flight for the target area, and it will take off, do the measurement, and come back and land, and you don't need to touch any bottom. So this is a very convenient way to collect data. This is okay. So this is a time lapse of one of our aerial data collection on a tomato field. This tomato field is infested with weed that's called bromelain, and it's attacking it's not on the ground, it's under the ground, and it's attacking the roots. And we are using hyperspectral to see if we can detect this before it appears and before it makes the damage using the non-visible band. So this is a hyperspectral camera that is going and come back and scanning this field. And after that, we can use a very simple multispectral camera as well for collecting the data. So I thought, since this is a tomato and there is a lot of tomato in Chile, that might be interesting for you. But this is a 2 hour of field data collection, and that is shown to you in 1 minute. So okay, so I talked a little bit about the data collection. Now I'm going to talk a little bit about the calibration. We have to do a lot of calibration to our data before start processing them. One of those calibration that is usually ignored by many companies and applicators in remote sensing, and we realize that that's important to do before any step, is radiometric calibration. So what is radiometric calibration? When we use a sensor, the sensor has some adjustment. For example, we can adjust the gain and we can adjust the exposure time. And based on that, the values that the sensor measures varies. So if the light is changing during the data collection, that values changes also. But that doesn't mean that the actual value on the plant is changing. So we need to find a procedure to take care of those variability in the data. Sensors usually record in digital number. That means just the voltage that a sensor measures, but we need to convert that to reflectance. To do that, we first need to convert them to absolute radiance, and then we need to convert them to reflectance. This middle part, converting to radiance and then converting to reflectance, is usually ignored by many application. And let me show you what happens if we ignore them. So we did a test on three different gray, four different gray tarp on the ground, 24% 24% light, 12% light, and 6% light. And we wanted to see if we can get that values in the aerial images. So this is a result we get with different camera settings if we don't do conversion to reflectance. So if we don't do it, the radiance conversion, we can see that the values would be different depending on the camera setting. So we don't know which camera setting we should use. If we use this, and the next time we use this, these two, although they are from the same field, they are not comparable because we can see different values. These three dots should be matched to these three dotted lines, but none of them has been like that. But if we first convert them to radiance and then convert them to reflectance, we can see that regardless of what camera setting we have, we always have similar normalized data set. This is something that we can use confidently in our data processing. This is something that will result in a wrong conclusion. So we should be careful about calibration. We have different type of calibration. Radiometric calibration is just one of them. These are some other methods. So we can use the reflectance of the tarp, or we can have another sensor on top of the drone to measure the variation in solar light during the flight, and then use that variation to adjust. And these are the, so any of this method we use, we will get a good result. If we use this method, we will not get a good result. The problem is 90% of people who are doing remote sensing is doing this, and this is wrong. Okay, so that's a little bit about the pre-processing. The next step is to extract features from orchard or from the data that we collect. So we have introduced a new technology that is called virtual orchard. Conventionally, people try to just do a spectral analysis of the data that they collect, so they didn't have the tools to measure the size of the canopy. There were some tools like LiDAR, but those are very expensive, not affordable for those. So there has been very little work on this. But we generated a method to first create 3D models of orchards, and then let me see. First create 3D models of orchard, and then extract information. Let me show you a clip about this. Okay, I'm not sure if, can you see my screen with the YouTube? Right?
Yes, I can see your screen. Perfect.
Okay, so this is a virtual orchard. This is a 3D model of a citrus orchard that is generated using photogrammetry. So in this case, we use the aerial imagery, aerial RGB imagery, but we collect them with an oblique angle to the ground. We usually do nadir imagery, but in this case, we do oblique because we want to see the side of the canopy, and by using photogrammetry technique, we can stitch all of these images to generate something called densified point cloud. So, for example, this is how it looks like. So we can see that it's a very precise 3D model of an orchard. It can be used for different applications. For example, you can navigate a robot within an orchard, something like this, and you can see in the lower right the path that is navigating. We can also generate these 3D models in non-visible bands. For example, this is an almond orchard. Then this is a 3D model in near infrared, so we can see the reflectance in non-visible band from the side of the orchards. So this is in another band in the red edge from the same orchards. But let me see how we can use that. One thing that is important for example, water management is to have a good estimation of canopy light interception. Canopy light interception is correlated to yield, to water requirement, and to, for example, how much nitrogen we can. So the way to measure the light interception is to look at the shaded area on the ground, right, under the ground, and see if we have a bigger shade, that means we have a bigger canopy. To do that, we run a light bar, a ground vehicle with light sensor on that to see where it's light, where it's dark, and where it's not, and then have an estimation of how much light is intercepted by the entire orchard. And that would give us some estimation of how much yield, for example, we can obtain. But that's a value for the entire orchard. It's important for us to do this measurement per tree. And using this photogrammetry technique, we can do these measurements per tree. So for example, we can measure plant height, we can measure canopy cover. Canopy cover is something that we assume is highly correlated to part interception, and we can do that measurement per tree. So there are more videos about different type of virtual orchard. For example, this is a vineyard. I guess, yeah, this is a vineyard, and this is a date palm orchard in Southern California. This is a pistachio orchard. This is a commercial pistachio orchard, and yes. So one interesting thing, if you see some area for missing trees, you can observe that virtually in your office. You don't have to go to the field to see what's going on. Okay, so that's virtual orchard. Now let's see what we do with this virtual orchard. So as I said, virtual orchard is a 3D point cloud representation of the orchard. What we can extract from that is a digital surface model. Digital surface model is a matrix, or is an image in which each pixel has the height information of the corresponding point on the ground. So for example, this is a digital surface model, and we can see the height variation on the ground. So definitely trees and pixels belonging to trees have higher height. So we can see them clearly and segment them from the ground. We know that there are some known planting patterns. So orchards are planted on a square or double. And if we know the planting pattern, if we know the tree spacing, and we know the row spacing, we can just find the center of each tree by locating the three points that for the top left tree, top right tree, and bottom left tree. If we just locate this, we can generate points for all the trees. And then when we have the center trees, we can make a bounding box for each tree. That's the allocated area for each individual plant. So this is a better representation of what we are doing. So there is a blue rectangle, that's the allocated area for the plant, and the green polygon, that's the actual area of that allocated area that's occupied by the plant. That's the best and easiest indication of the plant size that we can correlate to a lot of features, and I'll talk about it here. So what we can extract from this, first of all, we can extract canopy cover, percentage of this rectangle that is covered by the canopy, but we can also calculate an index of the volume that is a more accurate representation of canopy size, because it also includes the height information. So let's see how it works. So this is a point cloud from the side view, and this would be the maximum height, the tallest or highest point on the tree, the average height, and here we can calculate canopy cover and canopy volume. So canopy cover I already explained, but let's see what we call canopy volume. So if we show a 3D model, this is actually the DSM, right? So DSM has the information of the crown of the tree, but we know the altitude of the ground, so we can see, we can estimate the space underneath this kind of canopy crown, and that would be an indication of canopy size. That's how we calculate canopy volume using photogrammetry technique. But we wanted to know how accurate this measurement is, because we never know what would be the actual volume of the tree until we take it out and put it in a big container with water and see the difference in water move, changing the water height. We can't do that. So the next best is to use a LiDAR. LiDAR provides the best 3D model, the most accurate 3D model of an orchard, but LiDAR is a very expensive sensor. It can cost more than $300,000 for an aerial platform. So it's not something that everyone can use. But with the photogrammetry technique, with $1,000, less than $1,000 drone, you can generate very similar point cloud data set. So here on the left, you can see a point cloud of a tree generated by LiDAR, and on the right, you can see the same point cloud generated by photogrammetry. This is also another comparison. This is a side view of an orchard, 1 meter thickness by LiDAR and by photogrammetry. So LiDAR can penetrate into the canopy and see actually the points hidden within the canopy. Photogrammetry cannot do that, because photogrammetry, in photogrammetry, we just look at the images. So whatever visible in the image, we can stitch that and estimate the distance and measure the height. So that's why when comparing the LiDAR and photogrammetry, we can see there are a lot of missing points within the canopy. But is that really important? let's take a look at. This is also another 3D model representation of point cloud generated by LiDAR and photogrammetry. We can see they look very similar. We used a method to calculate volume using LiDAR data and also photogrammetry and see how they match. So this is one method. It's called voxel. And this is the same tree created by LiDAR and photogrammetry. And we can see they have very similar. We have done some statistical analysis, and photogrammetry and LiDAR have more than 90% correlation. So less than $1,000, more than $200,000. Very similar result. That's the beauty of technology, that every day we have a new technology. That's something that was impossible for us last year. It's very possible this year. All right, so I think now it's a good time to talk a little bit about the case studies, and then we can have a session for questions. But if you have any question during this presentation, please let me know. The first case study we are working on is a project supported by the almond board of California, and in this project we want to predict almond yield early in the season. What is the conventional method? So as I mentioned, canopy par interception or canopy light interception is highly correlated to yield, nutrition, and water consumption. So if we have a good estimation of par interception, we can do some mapping and find out what's going on, and also find out what how much yield we are gonna have. This is a light bar that actually mounted on a Gator vehicle, and it has an array of light sensors. So if there is a shade, light sensor doesn't get anything. If there is no shade, it gets something. It has a GPS here. So all the points are georeferenced, and after the data collected, we can measure the canopy par interception for an entire row. This is the study that correlates the midday par interception, usually measured in June, July, to the actual yield. And we can see that this is for a lot of data from 2009, 2016, and for different nuts, including almond, pistachio, walnut. And Bruce Lempenen in the plant science department has come up with this model that for each % of par interception, we can expect about around 55 pound per acre of almond kernel meal. So that's a very good functioning optimum orchard. If we don't get that yield, that means our orchard is not optimal. And we can see many orchards in California that have been scanned, they are not functioning optimal. There are also some very good orchards that are very well managed, but the objective actually here for all these points is to get to this. And if they can get to this line, they can maximize their yield, they can maximize their profit. Excuse me. This is a very good method, but it's slow. You need to have this machine. We only have 2 of them in California. And you have to run that in solar noon. That means between 11 a.m. to 1 p.m. So that's all the time you have. That is a lot of limitation. And later we also see that it's not very accurate as well. So what we did, we scanned 3 almond orchards 5 times during the season. And at the end of season, we measured yield per every single tree. So in total, we had about 1,100 trees in the tree experimental plot. So you can imagine how much time we have spent to do data, their yield measurement per tree. So this is how the almond yield is measured. So we put a tarp underneath the tree that has been harvested. Then we collect all the wet yield and weigh them on a scale. So we knew the wet yield per tree. Then we come up with the equation to find the dry yield, and we use that for our data analysis. Okay, so this is an overview of data analysis that I will explain it. It's a lot of information, so let me explain what's happening here. As I mentioned, we did 5 times data collection. We removed the first time, so this is data collection in May, June, July, and August. We calculated canopy cover and volume index for each individual tree. And also we had the canopy light interception measured using this tool in June. And here are the results. We can see that the best result we could get using this conventional method is R-square of 0.214. But in the same date, using canopy cover from aerial imaging, we can achieve more than 2.5 times better R-square and a smaller error. So this is an easier method. It just requires some expertise and some background knowledge compared to the conventional method. And let's look at individual graphs separately. So this is PAR, or canopy light interception with yield, and as I said, the best R-square is 0.214. And here is the optimum orchard. We can see all of these orchards performed not as good as an optimum orchard, and we can estimate yield by 424 pound per acre error. But compare this with canopy cover versus yield. So first of all, the R-square improved significantly, then the error decreased significantly. And one thing that I wanted to mention is that although we tried different genotype of almond, one genotype is the major genotype, and that's non-pearl. And if you look at here, for non-pearl only, we can get an R-square of 0.82. That's an amazing prediction model. We do not expect remote sensing to give us accuracy more than 70–75%, because it cannot definitely do the magic for us. But here, only using single feature, we can get that R-square. That's amazing result. And we are working on this to improve that. The second case study that I'm gonna talk about is for table grape actually, and we want to monitor nutrition status in table grape. So for this research, we selected a vineyard, and we created some experimental plots in which we applied different amount of nitrogen to this plot, to each of these plots. For applied no nitrogen, replacement nitrogen from last year, and 2.5 times of replacement from last year. Then we sampled, so each block included 5 vines, and we sampled each vine separately for nitrogen. We knew the nitrogen status of each vine separately. And I don't Yeah, so this is how the measurement has been done in the field. So we see people are taking samples from each individual vine, leaf sample and tissue sample, and then we examine them in a lab and we know the exact nitrogen content for each vine. So these are the histogram of different nitrogen level within that block. We were able to generate deficient nitrogen, excess nitrogen, and optimum classes. So basically, we wanted to compare very deficient nitrogen to excess nitrogen vines and see how they are different in the aerial multispectral imaging. So first of all, this is a signature of multispectral signature of deficient versus excess. We can see that this is green, 560, this is blue, and this is red. We can see that in the green area, the deficient leaf sample reflect more light. It means that if we have deficient nitrogen deficient vine, the leaf will appear with lighter green. So this is what we can see. In the red and blue, we can see there is no difference. So we cannot use that. This is red edge and this is near infrared. We can see that the same thing happens in the red edge as well. Deficient nitrogen reflect more, but in near infrared, we can see that deficient reflect much less. So these knowledge can be used to classify all the vines in the vineyard and use that as a decision support tool. So let's see the regression model. So this is a regression model using a machine learning algorithm called XGBoost, in which we employ all 5 bands of multispectral sensor into the model, and it will give us a predicted nitrogen. So what is the input is blue, green, red, red edge, near infrared. The output is how much nitrogen is within that vine. How awesome is that? And this is the predicted nitrogen, and this is the measured nitrogen, and we can see they are highly correlated. If you want to do that for entire vineyard, it means that you need to sample all vines, send them to lab, spend a lot of money, maybe more than what you can profit, just to know how is the nitrogen level of the entire orchard. But using remote sensing, you can scan the vineyard, just do a few sampling, and based on that, calibrate your model, and then you have the nitrogen status for the entire orchard. This is some more in-depth details. These are vines with different nitrogen level. And I compare Ndvi, NDRE, and a model that we developed using a machine learning algorithm. So on the left, you can see mostly deficient samples, and on the right, you can see optimum and excess. For example, this is an excess, and we can see that it appears completely green in classification. But Ndvi, if you compare this Ndvi, this Ndvi with like 2.52, which is less than that, there are not much distinctive difference. NDRE is also another index that is mostly used for nitrogen. So NDRE and Ndvi, these are the conventional remote sensing method. And we realize that it's not very helpful. We can use AI model, artificial intelligence model, and get much more accurate models. How can we use this? So we are developing, this is old slide, so the website that we are developing is actually myvirtualorchard.com. But I just want to walk you through how this can be used. So if we have a grower that has a drone, they can just fly the drone with the instruction that is provided by our lab and upload all the imagery. So then they can go to this website. This is not the actual website. This is just for the presentation. Select, for example, your area, zoom on the area, and then you can start uploading your imagery. You can pre-process them and upload them then, or you can upload, just take out the SD card from the drone and upload everything to the cloud. Well, first we will have an updated aerial view of the vineyard. Then we can generate the 3D model, add the 3D model, generate the digital surface model, and add the digital surface model. So comparing these to the other image, this shows a slope actually in the field. So the color map shows, for example, this is the higher altitude area and this is the lower altitude area. Then we can process digital surface model, find individual vines and segment them. The next step, we can add multispectral imagery and any other type of imagery that we have. For example, this is the thermal imagery of the same orchard. And then we need to run the prediction model. So that's all the steps we need to do. It's very easy. It can be done less than 2 minutes. This is the result. So what is this? This result shows the area in your vineyard that you have deficiency, the area that has optimum, and the area that has excess nitrogen. So all these red area, and we can see most of them are in the edge of the orchard, they have deficient nitrogen based on the model. But again, this application and remote sensing doesn't need to replace growers for decision making. It doesn't make a decision for you. It just gives you an insight of what's going on. The growers will be the one who make the decision. So these thresholds here for optimum, excess, and deficient can be modified based on growers' preference. For example, if you want to be a little bit conservative, you can move, or let's see, let's go to our. So if you are confident that, for example, you don't get much loss from nitrogen deficiency, you can change these two bars to the left, and then you will have less deficient area, more optimum and excess area. If you want to become a little bit conservative, you want to make sure that all vines receive enough nitrogen, you can change these bars to the right. So that shows more area that might be deficient. So I think this will be very good information for the growers during the season. Okay, so the next case study that I'm going to talk about is about predicting yield, fruit quality, and nutrition status in citrus. That is a project supported by California Department of Ag and Agriculture. So let's see what's going on here. Okay, so in this research, we had 6 blocks, 3 mandarin and 3 oranges, and we collected temporal data using these 4 different platforms: RGB, multispectral, LiDAR, and hyperspectral. I did not talk about hyperspectral because I thought it might be irrelevant. It's more a research tool, but if you have questions, we can discuss about it later. So in this study, we did not measure yield per all trees. We just selected a few trees and measured the yield for them. So this is, for example, 1 block of the 6 block, and we can see about 9 trees have been sampled in this. So for each harvested tree, we calculated weight, volume, and number of fruits, weight of each fruit, volume of each fruit, and number of fruit, and total yield, color fruit. We measured a lot of features from the yield, and we wanted to see which one we can predict using the aerial imagery. So this is again some data processing. We find individual tree using DSM or mosaic, and then we segment each tree separately. We calculate canopy cover. For multispectral data, we had to deal with the shadow problem. So the shadow area within the mandarin canopy, there is a hole in between that makes a shadow. So we get rid of all those shadows. So we had the reliable multispectral data, and this is the mask. We measured per channel mean, standard deviation, minimum and maximum. For thermal, we did a similar procedure, masked the thermal raster, so we knew the pixel values belonging to each tree, not the ground or other objects. So in this project, we fused different type of information. We fused multispectral, profile, and thermal data. And this is a model that we created for predicting citrus yield. We could get about 59.59 R² for predicting yield, which is very good, very similar to almond. And that again proved that the use of new tools that we use in remote sensing for specialty crop. Okay, so that's for yield. We can also predict number of citrus fruit per tree with even better prediction accuracy, and about 72%. And we could also estimate yield volume. So this is all way in advance before the harvest time. So these orchards have been harvested in January and February, but we had all this information in mid-season. So that's, I think, a very good, valuable information for growers to have. Okay, so with that, I conclude my presentation today. I think it might be a long presentation, so I hope it doesn't bore you, but I'm here available to answer questions if you have any. Thank you.
Thank you very much, Ali, for that very interesting presentation. I'm sure there would be a lot of comments and questions. So I'll just give a brief closure to your presentation in Spanish and open to the questions. Así que bueno, para todos nuestra audiencia acá en Chile, queda ahora el espacio de las preguntas. La idea es que ustedes puedan o escribir las preguntas a través del chat, o si alguien quiere hacer una pregunta directamente, puede ser en español o en inglés. Vamos a estar aquí haciendo el apoyo para la traducción para Ali. Creo que esta presentación realmente ha sido muchísima información, nos tiene que dar tiempo también a nosotros para digerirla, pero sin duda nos queda claro que la adopción de estas tecnologías es un ciclo donde vamos a ir retroalimentando toda esta captura de datos, la construcción de modelos de confianza que nos permitan generar este conocimiento accionable y práctico. Así que doy la palabra para quienes quieran levantar alguna pregunta. La Natalia les va a quitar el silencio, si no lo pueden escribir a través del chat. Okay, So Ali, we have the first question here. I'm just going to make the translation for you.
Okay.
Lo leo para todos. El Virtual Orchard es un procesamiento en tiempo real y el granjero puede conocer la información inmediatamente. Perfecto. So this question refers to Virtual Orchard project that you mentioned, and it says, are you getting the information like in the real time as you're capturing the information in the farm? Is the person that has the remote sensing data dashboard, are you getting that information immediately, or you need like a time for that to be processed?
So for Virtual Orchard, we can and we cannot. So the new drone, for example, that we get is a multi-spectral drone, and you just look at the spectral image, and you have a monitor that you can look at the Ndvi or different indexes in the live view. But for Virtual Orchard, we are collecting imagery in oblique angle, and we need to have all the images before processing. And usually processing for point cloud takes, depending on the power of computer, takes between 1 hour to 1 day.
16 pallets, de los cuales son 7 este gallo, habría 9, pero yo creo que no los va a sacar, ¿eh? Y después tengo
Mariano, creo que tiene
un
su
clima
micrófono abierto.
Ya, pero esto tengo que preguntarle a José Tomás si lo está sacando. 22 kilos granel.
Okay.
Sorry for that.
No worries. So for making 3D models, probably not. It's not possible. And actually, we don't need to have real-time imagery, the real-time results, because there are some processing and calibration, as I mentioned. But we can have the results within 1 day.
Okay.
So the web application that we are working on is an automated processing, pre-processing, and analytics. So there will be no human involved, and everything will be done in the cloud. And we will have a very powerful server. So that would take even less when the My Virtual Orchard website is up and running.
Thank you very much. Así que, bueno, Javier, espero que haya quedado resuelta la pregunta. No es inmediato, puede tomar a un día, pero todo está siendo automatizado de forma remota y a través de estas herramientas, sin la necesidad que alguien manualmente tenga que estar haciendo esos análisis. Tenemos una pregunta de Jimena Solari. So we have another question. I'm going to read it in Spanish again and then make the translation. ¿Se está aplicando también esta tecnología a control de plagas? Por ejemplo, detección temprana. Okay, so how are these digital technologies able to help us with the like IPM and plague and disease control early on in the farm?
I did talk a little about disease control, but we have worked on this before. So there are different applications. For diseases, for example, very serious diseases like citrus huang-lang-bing or citrus greening disease, it's really, really important that you detect the disease before the symptoms shows up. Because when the symptoms shows up, it's already late and you're losing a lot of trees. And for some disease like citrus greening, there is no cure. So you need to get rid of the tree. In that case, remote sensing would be actually very beneficial because it can monitor the plants in non-visible band, something. So what we call symptomatic, it's something that we can see with our eyes. If we cannot see that, it's asymptomatic, but it doesn't mean that it's not there. It's there, we can see that. Using these cameras, we are able to, if not make sure, but at least predict which part of the orchard or which trees are more susceptible to this disease. And if we have that, we can go and find those trees, sample them, and do PCR tests or any diagnosis to see what's going on And so remote sensing digital agricultural tools, they are able to give us early warning before it gets late for diseases and for also insect or pest damages. So yeah, for example, one project that we are having right now is to monitor 2 spotted spider mite in strawberry and almond. And I know spider mite is a problem for a lot of crops, for avocado. So, but they are very tiny. You cannot see them with your eye, and they are in the back of the leaf. So even you have to have a magnifier or some tools. So we are developing tools. They are not remote, they are handheld, but it's easy to monitor and do a lot of sampling in short amount of time. If you have more data, you can make a better decision because you have more interpretation. I hope I answered that question.
Mm-hmm. Thank you very much.
And you need
Ali.
to translate that, right? So maybe I should stop. Don't have a long sentence.
Perfect. Entonces, para Jimena, nos quedó claro la respuesta de Ali, es que las cámaras y los sensores nos permiten predecir zonas del cultivo que son más susceptibles a enfermedades y justamente levantar estas alarmas para una detección de pestes más tempranas y hacer ese análisis de diagnóstico a las plantas específicas que identificamos que son sintomáticas a través de estas herramientas que no son visibles al ojo humano. So Ali, we have one more question here from Leticia Rojas.
Sure.
La leo primero en español. ¿Las imágenes permiten ver la condición hídrica de la planta para riego diferenciado? So, are these virtual images that you're capturing with these technologies able to give you information about the hydric, like water content condition of the plants, so you can make a decision about where and when to add the water?
Well, actually, that's an area that has been worked on a lot. So many people have already worked on that and realized that there are already models that based on aerial imaging for irrigation scheduling that combines like use of evapotranspiration, information from local sites with climate data and aerial data. So combining all of them, that will give you daily ET for irrigation. What we are doing is we have a project with Walnut, and we monitor. We take the aerial images. At the same time, we use a pressure bomb to measure the stem water potential for the target plants. And so we are trying to see that's the best measurement of how healthy the plant is, and we are trying to correlate those data. But water management is an area that has been worked a lot. There are already models in that, so that's not our focus right now, because we are trying to make models for something that is not available right now. But that's also part of the data that we can not research more, but we can maybe extend more.
Thank you very much. Perfecto. Entonces, Leticia, nos queda claro que ya existen varios modelos anteriores que combinan los datos satelitales, datos aéreos, con los datos de estatus hídrico de la planta mediante bombas de presión. Ali nos comenta de un proyecto que hicieron con nueces, pero que hoy día ellos justamente están poniendo los esfuerzos en herramientas donde no exista tanto desarrollo previo. Okay, so more questions are coming here, Ali. So
Okay.
Stanley is asking.
Olivia, perdona. Olivia, perdona. Andrés
Sí.
Olivos está hace rato con su mano levantada, de Olivos Innova.
Ay, perdón. Ok, démosle la palabra a Andrés y después seguimos con la pregunta de Stanley, Christian y Juliana para terminar.
Thank you, Olivia. Hi, Ali. Thank you very much for your presentation. I've been following your work from a while through Twitter and your website. I'm really impressed. And I have two questions for you. The first one is, is anyone in California using remote sensing for actual orchard practices and decisions? I mean, changing traditional measurements for remote sensor measurements. Like, I don't know, just in my mind, I have like, if you measure canopy volume prior and spraying application, then you can do like a variable rate application in order from the data that you get from the canopy volume, or maybe a LiDAR for yield estimation or something like that. Have you seen like a grower using remote sensing for their decisions?
Yes. So thank you, Olivia, for your question. Actually, there are some growers that they have either some younger employee or they are younger, so they're eager about technology and they're using drones in their orchards. But if there is a product available off the shelf that can people go and subscribe to manage using remote sensing, I don't think such a thing is available right now. There are a lot of companies like Corteva or some local companies who are going to that direction, because basically there is a lot of opportunity and there's a lot of money in that area. But still, it's soon to growers to adopt that. I mean, it's not soon, but they have not adopted that yet. There are some reasons for that. First reason is that many of these companies that provide services, they have models that are not very well calibrated. So usually they are using models that are calibrated in the Midwest, for example, corn, soybean. That wouldn't work for tomato or almond. Or using some general indices like Ndvi. Ndvi correlates to everything. It correlates to yield, to disease, to water, to nutrition. But it doesn't make a strong correlation. So that means Ndvi just gives you an overall estimation of plant health, overall how the plant is doing, but not detailed information. So back to your question about precise spraying. Yes, definitely that would be a good measurement for adjusting the sprayer, or maybe shutting down some nozzles during the row if they get to a less dense canopy or shorter canopy. But I don't see that people use that for citrus, basically because in citrus they are trying to keep the entire orchard uniform. So we can expect that at least all the trees have the same height because they are topped, and maybe there are not that much variability to address with a sprayer. And if there is, there are like more immediate problems with the spraying that are more important than this. So maybe this is not a priority. For example, drift and deposition, these are two major problems with spraying that the growers are dealing with, especially for citrus that has a dense canopy and it's hard for droplets to get into. But I see some application like 3C, for example, a smart sprayer that use ultrasound data. So yeah, I can say that would be a future application of this technology, but there are more immediate applications like nitrogen. So what I realize is nitrogen management, water management, and predicting yield. These are the three main major problems that can be solved with remote sensing. These are the low-hanging fruit. So we can get that in 2-3 years. Other than that, there will be more time. Yep.
Thank you very much, Ali. Just for the sake of time, and we know that this invitation was until 1:30. Okay. We do have 4 more questions, and I can see there's a tremendous interest in your presentation. So I will make a suggestion. Just let's end up with one last question, and then I will send you the other questions so we can follow up with everybody, so we could actually give you the answers. Is that okay for you, Ali?
Absolutely, sure, yes.
Perfect. So let me go with asking, would you need to take ground data for every orchard for different growers before applying the models to make inferences through digital ag and virtual orchard, for example, for yield?
So first of all, we need to find out if there is any correlation between yield and aerial data. That's why we do different orchards and different genotype to see if we can come up with a general model. We realize that that's really hard to achieve, like a model that works for table grape in Chile and also work for wine grape in California. There is a lot of unknown factors that we don't know. There is many we know, but there is a lot that we don't know. So my approach for this is to always have some ground truth data to adjust the model for the specific geographic location and a specific genotype and a specific stress for that location we need to take into account. We can ignore that, but I can say if we do that, we will have more confidence in the result.
Perfect. Thank you very much, Ali. I think we would definitely have more questions as the people are digesting this amount of information, but I want to thank you for this great presentation. I will open the invitation for everybody to go to the My Virtual Orchard website and check a little bit more about your work. We will follow up with the participants, so let me switch to the Spanish. Agradecer a todos los que participaron, de verdad tuvimos una muy buena convocatoria. Les vamos a enviar a todos la presentación de Ali y por favor para Stanley y Catalina, personalmente voy a enviarle sus preguntas a Ali para poder contestarles a todas esas nuevas preguntas también que surgieron aquí de Gajardo y también algunas finales. Así que agradecerle a todos por la participación. Esperamos seguir continuando con estas charlas técnicas y haciendo un poco el puente entre las capacidades y todos estos desarrollos que están ocurriendo en California y visibilizar esos esfuerzos en Chile. Yo creo que hoy día el tema fue de gran interés. Nos damos cuenta de que hoy día se abre un potencial de aprovechar todas estas tecnologías para tener este conocimiento accionable y práctico. Así que gracias a todos, hora de almuerzo, estaremos en contacto.